What's up? Sorry? Oh, yeah, we can hear you. Sorry, my bad.
Luck holds out, and many thanks to everyone who just got shuffled around. I am hearing myself, so I don't know if there's a mic to mute, but if not, we can deal with that. And let's just get into it, shall we? And hope that everything holds out for us. All right, so I'm Evan, of course, and what I'd like to talk about today is using miniKanren to build something like this. To do MVC is a browser-based standardized application. It's been implemented in hundreds of different JavaScript libraries and frameworks as a means to compare them. Now, since we won't have time to go through the whole implementation, what we're going to do today is implement micro to do MVC. Here we are, which is a to-do list so underfeatured that we can implement it in the space of this talk using miniKanren. Now we have here a 2-item to-do list that not coincidentally lists the 2 main sections we're going to cover today. So let's get right to it. This talk is divided into 3 sections. So the first of which is just I'd like to take a moment to address the elephant in the room, namely, why are we developing to-do lists in miniKanren when there are so many existing JavaScript solutions? And after that, we're going to build micro to do MVC in 2 parts corresponding to the 2 big problems that this miniKanren web framework tackles. The first is taking our application's data model and rendering dynamic HTML from it that stays in sync with the model when it changes, hence model to view. And the second is defining update events in the HTML view that transform our data model across application time steps, so hence view to model. And I'll say in advance that although I will try to keep this talk accessible, you will probably get more out of it if you are familiar with modern JavaScript web development. But because this is such an unusual application of miniKanren, it is involved really bending the underlying miniKanren architecture into new shapes that I'll talk about, and that I suspect may have applications to other areas. So hopefully there'll at least be something of interest for everyone in this talk. Now then, why the web and why miniKanren? Over the past decade plus, there have been literally thousands of new JavaScript frameworks, most of which never gain any traction to the point that it's become something of a meme. Yet the fact that these frameworks keep being produced and that new frameworks periodically do gain traction and become major players suggests that there are still problems in this area that aren't fully being addressed. This talk comes out of an intuition that I've had for a while that the structure of miniKanren's architecture seems to me to fit well with the kinds of problems that all of these frameworks are still struggling to solve. So while it is still early in this research and it remains to be seen whether miniKanren will conquer the web, I'm not going to therefore try to convince you today that miniKanren builds better web applications and other frameworks necessarily. What I can offer, I think, is an exploration of my attempts to find the most natural ways to express graphical interface logic in miniKanren, and an analysis of what I think are some promising harmonies between miniKanren and this problem space that have emerged from these attempts and that signal to me that this is an avenue worth further exploration. So in that spirit, let's build a to-do list in miniKanren and just see what stands out to us about the potential for relational web application design. So let's start with the simplest possible to-do list, a static page with a single hard-coded to-do item. So on the bottom, we see the HTML output of our program, 1 paragraph HTML element containing body text telling us to implement the piece that generates the HTML based on the application data. So since this is just static text, we generate this HTML page using a template seen here on the top half of the slide, written in a special S-expression-based templating sublanguage embedded in JavaScript. This template is just a JavaScript array where the first element defines the parent tag, and in this case the paragraph, and all the subsequent array elements are appended as child nodes. So here the JavaScript object there represents the paragraph, and the string is a single child text node of that HTML element. If we want to render an arbitrarily complex static HTML page, we can just give the framework an arbitrarily complex JavaScript array mirroring HTML's nested structure. We don't need miniKanren for that. But to make this display dynamic data, we need to replace any subcomponents of the overall page template with miniKanren goals. So let's see what that's going to look like. In this case, we're going to replace that entire JavaScript array template that you just saw, that entire paragraph template with a miniKanren goal, which is represented here as a function that takes a single argument. That argument is a logic variable that we'll call the view variable, and that function needs to return a first order miniKanren goal that uses that binds that view variable. So in this case, our return goal unifies the view variable using the EQ method of logic variables, which stands for unification, and it binds it to a static template from the previous slide. And a red here is going to indicate things that have changed as we go between slides. So whatever we bind that view variable to, the framework will walk the variable and replace this whole function template with whatever template that view variable walks to. So this just essentially reproduces that static HTML slide previous. So now let's add a little bit of data. So here model is a global logic variable that can be accessed in all of our miniKanren goals anywhere in the template. And we're going to initialize the application with a model bound to our to-do items string. So then in our template, we can replace the string with the model variable. And now whenever model changes, a new template will be swapped into the HTML document in place of the original function. And note that I've decided to delete the function signature in the return statement here for readability. That anywhere we see a variable named view, we should assume there's that function wrapping it. Now, of course, we never have just one thing on our to-do list. We want a list that can grow continuously as we add items to it. So let's start making actual use of the fact that we're in miniKanren and leverage some non-determinism. At the top here, we've turned the model from a string into a list of strings using scheme list syntax here for presentation purposes. And now looking at the code in the middle, instead of displaying the model directly, we introduce a fresh logic variable e for element, and we use member_o, the member_o method of logic variables, to bind e to each element in the list. Therefore, instead of binding view to a single template, it is non-deterministically bound to a series of templates, one for each answer returned by member_o. So then we're going to take the returned stream of answers from this miniKanren goal and append them as sibling elements in the document, creating the list of paragraphs that you see at the bottom. Now let me note parenthetically that we are implicitly using a depth-first search and a run star type semantics here, so the order of the paragraphs will be somewhat predictable, and we do have other mechanisms for controlling order that I won't get to in this presentation. There's no way to do a run one type semantics to really pick a non-deterministic interface, but that's something that I'm trying to research. So back to the problem at hand. I think using non-determinism for dynamic elements here is a relatively clean alignment between miniKanren and the problem of iteration here, but why go to all that trouble, right? Why not some kind of simple list comprehension as is done in many other frameworks? So there are a couple of advantages here that I think miniKanren gives us. First, it's somewhat minor, but nevertheless useful, is that we can easily write recursive miniKanren goals that express things like hierarchical trees of HTML elements quite naturally, which is something that some frameworks that have built-in iteration functions struggle a little bit with. And there's an example of that in the paper, but more importantly, there's one big problem that we need to solve that we can leverage miniKanren's non-determinism to address in what I think is a kind of interesting new way. If we could just throw out the whole page and regenerate it from our data at every time step, it would be very easy to keep the data model in sync with the HTML view. But even ignoring efficiency concerns, browsers have local state like scroll bar offsets and text box focus that get lost when we do that. So what we really need is a surgical way to update the live HTML page in response to the pieces of the data that have changed. And to do that, we need to track which HTML elements correspond to which data. And that actually is a somewhat non-trivial problem, and it's in fact one of the main problems that most of the major frameworks attempt to solve. So what's commonly done is some variation on a strategy called virtual DOM. The basic idea is that we do completely regenerate a representation of the document, the whole HTML page, pictured on the bottom here, and then we compare it with the previous document pictured on the top to determine by some diff process the smallest changes that need to be made to bring the document into sync with the data. And the challenge here is that this generalized problem of diffing trees has something on the order of qubit complexity, and the most important heuristics that frameworks use to deal with that involve deriving unique identifiers from your data, which may not necessarily be possible if your model doesn't naturally furnish unique identifiers for every element of every list. So I wish I could go into more detail here, but in the interest of time, let's just take a look at the strategy, the implementation, underlying strategy that we can use in miniKanren here to get around some of these problems, which is a approach that I call the view tree. So think about this picture here as an abstract representation of the member-row operation from our running example applied to a two-length list. So the top node represents member-row destructuring the head of our list, which I'll assume is bound to the model logic variable. The second level is a condi binding the view to the first element of the list and destructuring the tail. The third level binds the view to the second element of the list and fails to destructure the nil tail of the list. So now, instead of treating this as a purely abstract concept visualization of a miniKanren search, let's build an actual in-memory representation of this tree. And we can do that by gathering up the first-order representations of all the unifications and constraints that we encounter. And every time we hit a condi, we create a branching node that stores the conjunction of all of those first-order constraints in the node itself. Successful answers and failures both generate leaf nodes. Now, into each leaf node, let's put an actual in-memory reference to the live HTML node built from that answer. So now we can rerun our search repeatedly with different starting substitutions by threading the substitution down through this tree and applying all the goals along the way. If a goal fails, we remove all the HTML nodes that are contained in subtree, headed by that node. And if a previously failing node succeeds, we insert its HTML nodes at the appropriate offset in the document. So now here's the key idea here. If nothing else in this section made sense, we are essentially using the position of an answer in the reified miniKanren search tree, not its order in the answer stream, which can change and which gets us back to diffing, but in the search tree itself as a unique form of identity for each answer. So more generally, we're building and modifying a reified search tree, and we're using it as an organizational structure for a stateful derivative of that search. That's the key idea here. So maybe that representation is a web app, as it is here. Maybe it's a debugger, where we can clearly see where the failures occurred and potentially trace the exact failing constraint if we wanted to, and rerun goals with different bindings, various ideas that have come up in working with this. So regardless, this view tree at least does the job for us of surgically updating the document, which is what we needed here. Every time we rerun the search, we know exactly how to update the document because it's keyed to the search tree. So that's the first thing we needed to implement here. We now have our to-do list displaying a dynamic number of items based on the to-dos we initialized it with. We've completed the first item, but we can't actually cross it off yet, so let's implement that next. First of all, let's review what we're trying to accomplish here. So we know that we have a global substitution with at least some model logic variable that's bound in some way to our application data that we use in all of our goals. Have some other logic variables that we were created with fresh and bound to pieces of that model to destructure it, to access it. And we want to find a good way to set up event handlers in the HTML in such a way that we can cleanly specify how a user action should evolve the model data from one time step to the next. So for our micro to-do MVC example, we're going to do the simplest possible thing I could think of, and we're going to make it so that whenever you click on an item, the to-do text gets replaced with the word done. So when we click on the item for the last section, we should end up with something that looks like this. Now, the way that we're going to do this is through a procedure that we'll call reactive unification. So here's our running example for micro to-do MVC. We've only added a property onClick to the paragraph tag, which sets up an event handler for the paragraph's click action. And the way that we've specified what the action does is that the event takes is by supplying a miniKanren goal, e.setDone. All changes to the model are specified as miniKanren goals, all of which include this reactive unification subgoal set, which is a property of logic variables. And roughly, you can imagine that this is going to set the string value bound to e to a new value done at the next time step of the application. Reactive unification is asymmetric, so the left-hand side specifies a variable at the next time step, and the right-hand side is a value from the present time step to which that value will be bound. In a sense, we'll make a little more precise later. So now with just this rough intuition, there are a number of undefined behaviors that come up here. And part of what I've really just been doing has been experimenting with defining these undefined behaviors in different ways and seeing what kinds of programming patterns emerge. So the paper has more detail about some of the properties I've tried to define, but right now I'm just going to give a quick overview of some of the emergent patterns that I think showcase some of the possible strengths of writing this update logic in this miniKanren style. Now the property on display in this example is that if we're working with primitive data like strings, every variable is automatically bidirectional. Anywhere we can reference E to display it to the view, we can also reference it to update it to a new value back in the model. And the same is true for any future fresh variables bound to E. They all write back to the same string value bound to E. Now suppose we wanted to add a button to mark all items as done. We can use miniKanren's query capabilities to find all the logic variables that we want to set, and then we can non-deterministically set them. And what this is going to do is gather up all of the reactive unifications from every answer returned by our update goal and apply them all one on top of the other. If two updates conflict in general, the update fails. If they partially overlap, they unify, hence reactive unification. Now suppose we want to delete all the entries that we just marked as done. We'll need two fresh variables, pair and cutter, and there are three sub-goals here. First, we iterate over all tails of the model, so that binds the pair variable to every cons pair and to the nil element in the model list. On the next line, we check that the pair has the text done, and at the same time, we also extract the cutter. And then finally, we reactively unify the pair with its cutter to essentially overwrite the pair with its tail and delete it from existence. So we're essentially mutating the list to clip out a pair, although we define this in such a way to avoid some of the problems that usually come along with these kinds of mutations in other languages. So for instance, mutation doesn't happen right away. So as in this example, we'll iterate the whole list normally, we'll build up all these mutable cuts, and then they'll all be applied simultaneously at the end of the time step. And they will also take one another into account so that in this instance, at least it does the right thing, quote unquote, that you would expect from what we're trying to write here. Now let's take a step back and just compare these patterns with some other approaches to this update problem. Comparing programming paradigms is obviously a highly subjective task just because there are so many varieties of every paradigm and so many ways to use each of them. So I'll have to request some charity from your interpretations here. This is just my very high level intuition, and the intention here is just to give you some points of comparison to think about how these approaches interrelate. So thinking about the task, consider the task of filtering our to-do list to only the not done items, and then inserting a new item into the middle of that list. So in a standard functional approach, we're going to append the head of the original list, the inserted element, and the tail of the original list. But where do we split the head and the tail, right? We're going to need to find the index in the original list of the item before or after the insertion point in the filtered list. And that means we need a stable notion of identity for list items, which if there may be duplicates means we need additional bookkeeping metadata, which comes at a complexity cost to the model. We could take a bidirectional optics-based approach where we insert directly into the filtered list, but because the position in the original list is ambiguous, the programmer will also need to somehow specify an update policy, which, as I understand it, is still a little bit of an open research question, and I've seen different solutions proposed for that. In the reactive unification case, we would include in our query the cons pair of the original list at which we wanted the insertion to happen, and then directly set it to a new pair. So one possible arguable advantage of this is that we're always relatively precise about exactly where in memory our new data is going. It's almost like, I shudder to say, almost pointers, but without some of the drawbacks that come with mutation happening instantly and affecting the structure of subsequent mutations. It's maybe arguably more of an intuitive, direct manipulation type of strategy. And I think the key idea here is that miniKanren is letting us replace data structures in many instances with queries. So functions that produce data structures in the usual functional programming sense are not necessarily bijective, and so when we try to turn them around, we encounter irresolvable ambiguities that we need to manually resolve somehow. When we filter a list here, that second list gives us a filtered interface to our data, but by being an actually fully realized list data structure, it raises questions about the semantics of list operations that introduce ambiguities relative to their source. So by contrast, a miniKanren query can also filter data, but it doesn't introduce a new data concept in the same way, or at least it introduces something different to the bidirectional programming equation. So now, as I said earlier, reactive unification, as I've defined it so far, is highly experimental. You could love it or you could hate it, and I'm not wedded to it one way or another, in the particular way that I've defined it. What I think is important here is how the underlying architecture of miniKanren gives us the affordances to experiment in this space, because that's the raw material that we're really all working with here, right? So I'd like to close this section by talking about how reactive unification is implemented. The key idea in this section is that with some modifications, the miniKanren substitution data structure can be used to track the provenance of data through our computations. And it can handle the bookkeeping for us that lets us do advanced types of bidirectional programming. So consider the case where model is a string, right? When we bind some new variable e to the model using ordinary unification, we could bind e directly to the string itself, and that's what we'd usually do in a search context. But we're going to change the usual behavior here a bit, and we're going to bind e to the model variable instead. Now we can still walk e to get to the string, but now e remembers exactly where that string came from, and so we can walk back from any reference to e to find the original model variable, and we can update the string value where it originally sat in the substitution, which will implicitly change the value of everything that walks to that same model variable. So to keep the C metaphor going a little bit, you can think of a model variable as an allocated secondary. When we set e, we overwrite the memory bound to model, but we don't change the pointers we use to identify that memory. So every time we unify two variables, we preserve that information by binding one to the other, so that the substitution tracks the provenance of every atom of data throughout the whole life of our computation and throughout the cycles of the interactive cycle with the user. So now, what happens if the model is bound to a complex term? How do we track provenance now? Let's normalize the substitution so that every atomic piece of data gets its own logic variable with its own physical storage, quote unquote physical storage here, right? So now we can independently track every string, every cons pair, every mutable piece of state in the model by referencing its unique logic variable and preserving the provenance of that reference throughout our relational computations. Glossing over a lot of details here, but this is the key idea for handling application state. We treat the substitution as a fine-grained physical storage device that gives every piece of state its own unique name and preserves those names across computations and unifications that let us walk back to the original source. So if we reactively overwrite this list with a new list, we essentially walk down these variables, overwrite their values in their final quote-unquote physical locations in the substitution while leaving the variable pointer structure in place. So model stays bound to x1 and x2. The value of x1 gets overwritten by a new primitive, maybe the string done, and maybe x2 will get overwritten by a nil list, and then the remainder of the list will be garbage collected or something like that. So in conclusion, we now have implemented micro to do MVC. We can go from a data model to a dynamically updating HTML document, and from user events in that document back to an updated application state. As I've mentioned, as I'm sure you can tell, this is a very preliminary report on an ongoing project. The code base itself is very rough at the moment, and many shortcuts were taken to get the paper examples running that will now need to be undone, but I do intend to keep exploring in this direction, and my intention is to make this eventually into a miniKanren-powered, production-ready JavaScript framework just to see how far miniKanren can go. So if you are interested in miniKanren for the web, feel free to reach out anytime. I've added a link to the repository in the last slide, but aside from that, I've got nothing else to say. So does anyone have any questions?
All right, let's thank Evan.
So a question on how the reactive update kind of thing works. In a situation, basically, would it break if I had a model and I had like two sublists in my model, and then I appended them with appendo before then rendering something? And then I tried to do a reactive update on one of the con cells, particularly in the first part of the list, that was sort of manipulated and reconstructed by the list append. Would that sort of still propagate back to the original list in the model?
So I would have to write that down to visualize exactly what operation you have in mind, but let me say a little bit more about how it works, and maybe that will give you some intuition about how to answer it, and I can answer it in more detail later if you're still interested. The simple way to think about what's happening here is that in most cases what will happen is we have a variable on the left side and we have a value on the right side, and very roughly what will happen in most cases is that we reify the value on the right side in the current substitution, and then we go overwrite the structure of the variable on the left with the values that we got out of that. So there are going to be, in order to preserve the reorderability of goals, there's no sense of time between two operations. So I don't know quite if this is what you had in mind, but if we're appending lists and mutating lists and then setting them to something, there's because the operations could be interpreted in either order, everything that we end up having to write has to sort of be a static operation. So you could append the lists and create some list in memory in the substitution bound to some variable, and then you could set it to some variable. But all the sets that we make have to be consistent concerning unification. The qualification that I'll make, and the most experimental part of this, is that when if we were to apply that logic to two elements in the same list, so we set, like we did earlier, we set one pair to something, we set another pair to something, those would theoretically generate two lists that don't unify, right? Because we've just told it to unify the tail with one longer list and then a subpart of the tail with a different list. So we handle recursive unifications like that, especially where we kind of start from the top and start overwriting, and then when we get to a more specific subpart of the list that has been directly set by a different reactive unification, we let that take over. And that's what lets us do something like non-deterministically walking the list and making a lot of cuts or making a lot of additions or changes, and it will still kind of build out some version of the right answer. And the last thing I'll say is that we should recognize that because the physical memory metaphor, when we write all the values into the list, the final normalized substitution has the form of a perfect tree. There are no shared references to anything, and that gives us a lot of flexibility too, in terms of not shooting ourselves in the foot. So if you still want, if that doesn't answer your question, let's get in touch afterward, and I can get a more concrete representation of what your question was and work out how it would happen.
Good, I'll talk to you offline.
Sure.
So maybe I'm not understanding something right, but HTML is a very ordered thing, right? Everything comes in an order, and in miniKanren, when we search for things, well, they do come back in an order, but it's sometimes hard to predict what it will be. Does that cause any problems with the HTML generation side of things here, this mismatch?
So currently, two things for that. First of all, we are running it with a depth-first search, and we are running everything run star. So everything is going to be relatively predictable in the sense that if we do member-o, and that's the first conjunct that we evaluate, things are going to happen in that member-o order because we're going to walk all the way to the bottom of the first member-o, get an answer before we come up to the second one. If we want to control the order, like sorting a list on a page, there's another mechanism for that I didn't talk about that basically involves our miniKanren goals, except not just a view variable, but also a order logic variable. And we can bind the order logic variable to some ordering key, and then it will step out and do a different process where it sorts and inserts thing in the right way. So I'm not using the traditional interleaving search for what I presented here, but I think there's a lot of possibility offered by experimenting with that, in the form that if I wanted to implement something that was a not run star semantic, so I wanted it not to display every to-do item in my list, but I wanted to simply pick one satisfying interface template and build an interface out of that. So I have a more intelligent automatic interface concept, maybe, where the programmer isn't as directly in control of every specifying constraints and letting the system generate a satisfying interface. I think that would be a really interesting thing to explore, and for that we would probably want the interleaving search, but I think in most cases I can think of, we'd be wanting to do a run one there. So again, we'd kind of still be okay on the order, because either we're doing everything in a deterministic order with a control variable that we can tweak, or we'd be getting one thing which doesn't have an order because it's only one thing. So if there's a use case in there for multiple things that are potentially infinite that we're run to, I haven't thought of an interface that needs that yet, but that could pose a problem.
Okay, thank you.
All right, let's thank Evan again.
I think we're probably at time.